The last topic we're going to look at with inductance, at least directly, we'll talk about indirect stuff with alternating currents in the next set of videos. But for right now, we'll end up thinking about the diagram that I ended up showing in the last set on your study notes. We'll have a potential difference source with connected to a switch and then connected to a capacitor. And then we'll have another side after that. We'll end up having an inductor coil and then another switch on that side. So what we'll do first, we're going to close switch 1, the one that connects the potential difference source and the capacitor, so the capacitor charges up. Same old stuff we've done a long time ago. So we know how much charge will set on there. Remember from the definition of capacitance, the charge that will set on that capacitor will be the capacitance times the potential difference. Again, there's no weirdness that's happening yet. There's a weirdness will come, but not yet. So now what I'm going to do, I'm going to open that switch, which basically effectively disconnects the battery. But I have charged the capacitor. And now I want to close switch 2. And I want to think about what's going to happen. So remember in the configuration I had shown there that since the potential difference source had the positive on the bottom, negative on the top, the terminals, then the capacitor will have positive charge on the bottom plate, negative charge on the top plate of the capacitor. So when I end up closing switch 2, after I've opened switch 1, so now I've only got the capacitor and inductor connected together, then what's going to start to try to happen, because we've talked about discharging a capacitor before, right? So what will want to happen is the charges would end up flowing from the positive side of the capacitor to the minus side, so they would cancel each other out, because that's where they want to go. So going downhill in energy. But that's going to end up causing a current, which was 0 before because the switch was open. It will start to cause current to flow through an inductor. And we've already talked about what happens when you do that. It will produce a back EMF. It's going to slow it down. Right? It doesn't win, but it will end up slowing it down. And so then as charge starts to end up flowing off your capacitor, it eventually speeds up, right? Because the amount of it's getting closer and closer to where it would be at equilibrium. So, or at least at steady state. And then it ends up, you've discharged your capacitor. But you've set up a magnetic field inside the inductor. And so when you do that, that's now set up a potential difference on the inductor. And remember, the inductor tries to fight a change in current. So the capacitor's through, as far as it would be sort of concerned, okay, it's discharged. But the inductor says, we still got current going, so it's going to keep trying to push current. So what will happen then is it will end up washing current back around the opposite way on your capacitor. And then it will charge up the capacitor, and then vice versa. So that's going to end up being what happens. So it ends up bouncing charges back and forth in this, and so we'll end up computing that, but that's sort of at a high level understanding why this is going to happen before we actually look at doing the math. We end up considering, so we've already got the charged capacitor. Again, the only reason I put that other stuff is so that we have charges on the capacitor. Once we charge the capacitor, we throw the battery away, we don't need it anymore. So we close the switch, and we're only really considering then the capacitor and inductor connected together. And we want to think about what's going to happen whenever we do so. So my capacitor has positive charge on the bottom plate, negative charge on the top. So it's got that potential difference. So the same potential difference is going to be on your inductor coil. Again, so because that's the only two things there, they're parallel to each other basically. So they end up having the same potential difference. And so that allows you to be able to figure out which way the charges will sit on the inductor coil, but also notice that that means that the inductor will end up pushing back against it, again, like what we already said. So everything there looks looks normal. So if we end up going around, sorry for some scratch on there. When we use Kirchhoff's first law, starting from that upper left corner, again, it doesn't matter where we start. We're just, we pick one direction. We've said that before. We pass through, so the total potential difference across your capacitor plus the total potential difference across your inductor, if you go around the loop, has to be 0 by Kirchhoff's first law. So we end up plugging in what those are. So potential difference across the capacitor is Q over C, right, from way, way back when. And potential difference across my inductor is going to be minus L di dt. Same old deal we've talked about earlier today. So those two add together give you 0. So that gives you Q over C minus L di dt equals 0. So on your notes. One of the things though to notice is, and it's one of the reasons back when I was telling you we have to be kind of careful. A lot of times you'll sort of talk about your current as being the first derivative of your charge, but you have to be careful to make sure that that is well defined. In terms of understanding why it might not be, remember we had the problem of what was the Q at all whenever we had a resistor connected to a battery, because what is the number that's increasing? There's not an obvious value for us to end up calling out. But here there is real charge in this circuit. There's charge that sits on the capacitors, capacitor plates. But the current that flows, notice whenever the charge goes down, the current goes up. So in other words, the current is produced in the direction in which the charge is decreasing. So in this situation, your current is minus the first derivative of the charge on the capacitor, which is the only charge there is in the system. So that's the reason why you then put in your current is minus the first derivative of the charge. So when you plug that in, you end up getting, after you clean it up a bit, you get second derivative of your charge plus 1 divided by LC times the charge will equal 0. And in order to solve an equation like this, that if you had Diffie Q's, this is old hat. If you haven't, it's a little bit more obscure as to where this comes from. But this idea of it bouncing back and forth should make it at least make sense that it could end up being something that's oscillatory. And that, so we'll end up looking for something that would end up being a sine or a cosine. And it turns out that in an equation of this type, you can end up expressing it as a sum of sines and cosines. Or you can use another trig identity to be able to say it's a constant times the sine, it could be the cosine, but everybody writes a sine, times the sine of your angle, and that your angle will be increasing with time. So we write it as an angular velocity times time plus theta 0, which again should sound a little bit familiar from stuff we did before. Now this is a completely different thing. This is not an alternating current generator, but this is producing something where you've got, in this case, charge that's oscillating back and forth in this type of way. Either by doing the explicit computation, or we can end up starting it, and then what I showed you with a proof, that what happens is the angular velocity of this oscillation, the number of radians per second, will equal the reciprocal of the square root of the product of your inductance and capacitance. And so that's called your angular velocity of natural oscillations in this. So you end up just having charge back and forth between your inductor and your capacitor. And if there's no resistance at all, of course, there's no, this is an idealization. So eventually, if you had any kind of real wires that are involved, even the real wires inside your inductor coil involved, it will eventually lose the energy to the environment by going through a resistor. But in principle, this can end up happening. It certainly can happen for a while, This is another effect that has a tendency most of the time not to be what you want to have happen. This ends up causing stray stuff going around that you may not be expecting. But this is where we end up getting this concept from. So that would end up being how you would find your angular velocity, which is again your angular frequency of oscillations, and that's the way it's always written in to describe what that frequency is. This ends up being basically a segue into what we're going to talk about next, which is a new topic. We're going to introduce alternating current, and that's where now we're going to have this oscillating, in this case, an EMF source, which we talked about in the last one. So we'll end up talking about what happens when you hook one of those things up to resistors, capacitors, inductors, combinations of them, and we'll end up seeing some important things that results in, and some things that we can glean out of that. So, and that's particularly important because if you're watching this, it's almost definitely the case that the reason you're able to see this is because somewhere upstream that alternating current was being produced. So you're seeing the effects of alternating current. So then I will break now and we'll talk about alternating current and the thing that at least in principle is next week's.